we're going to look at what determines the speed of the reaction. When you talk about kinetics, it's about the speed of the reaction. Okay, what are the factors that influence that speed? The factors that influence kinetics. Then we need to express the reaction rates. The reaction rate is the equation that tells you how fast a chemical is produced or consumed depending on the chemical reaction. And we have something called the rate law. The rate law gives you that mathematical equation that gives you information about the speed of the reaction. Then we're going to use a little calculus. And although we're not going to do integration, we're going to use the result of the calculus to get some neat equations. We're going to look at the methods of initial rate on how we can calculate the rate law based on some experiments that we do. The rate law is, as you can see, very important in kinetics. Then we're going to study specific orders: 0th order, 1st order, 2nd order. The order of the reaction depends on the concentration of the chemicals that are involved in the reaction. Okay, and then the rest of these right here is going to be part of the second part of our discussion: the kinetic molecular theory, the Arrhenius equation right here. And then we're going to wrap up the section based on the mechanism. Mechanism tells you the step-by-step process by which the chemicals mingles in order to form the product that you see. So this is an outline of what we are covering. So remember, I told you in the beginning of class that Chem 201 is like baby physical chemistry, baby PChem, because it tells you everything that the reaction will do, and the characteristics of that reaction. Tells you the efficiency, tells you whether or not the reaction will take place, or if you need energy. It tells you how fast the reaction is. And so when we talk about the efficiency of a reaction, or how much product is produced, we need to take a look at the thermodynamics and kinetics. Thermodynamics addresses whether the reaction will go or not. Will it take place? Yes or no. Kinetics tells you if it does take place, how quickly will you get there? And so if you take, for example, iron. Iron is a very common chemical, but we don't want it to rust, because when it rusts, the strength of iron starts to break down when it turns to iron oxide. So we want to prevent that reaction. It's very favorable thermodynamically, meaning that it'll take place. So what can we do so that it does not take place, so that we can slow it down? Well, we can address the kinetics. And usually what we can do to prevent iron from rusting is to prevent oxygen from reacting with the iron and forming iron oxide. Another example of thermodynamics and kinetics is your diamond. If you have a diamond ring or diamond jewelry, you can actually that can actually convert over to graphite thermodynamically. It's favorable. The reason why it doesn't is because there's a huge kinetic barrier between the diamond and the graphite. And yet we can use that knowledge to take graphite or just plain carbon, and under very high pressure overcome that activation barrier, so that we can take basically coal or just carbon and make artificial diamonds. We can do that, but we have to overcome the thermodynamics. So that just kind of gives you information about the chemistry that is involved, the chemistry that we are going to be looking at in the next chapter. So what are the factors that determines whether a reaction is fast? Well, diamonds can still be burned, yes, very much so. Tell you a little story about Lavoisier. Lavoisier was a chemist, very famous scientist back in the French Revolutionary War, I think. And what happened was he was the main scientist that established the law of conservation of mass. That is, the mass that you have before the reaction is equal to the mass after the reaction. What he did was he showed this through a series of experiments, but one of his major experiment, for those of you in Chem 152, you probably heard this story, but I'll say it here for the new ones. He actually recreated a historic event in which there was this Shah in the Middle East who had a lot of diamonds, and he put it in this vault, and the vault had a glass ceiling, and over time those diamonds started to disappear. Okay, and he kind of figured out what was going on with that, but the story goes that the Shah killed all the guards that was guarding those diamonds because he thought that they stole them. Anyway, what Lavoisier did was he took a big chunk of diamond. You know, diamond's not as precious as it should be. It's all based on the De Beers and how they associate it with marketing and all that. But anyway, diamond is a pure form of carbon in its tetrahedral geometry. And what Lavoisier did was he took that diamond and he put a huge magnifying glass on it, and he put intense heat on that diamond, and over time it disappeared. So if you have carbon in the presence of oxygen, because remember diamond is carbon, in the presence of oxygen, what products do you think you get? Yeah, it was a very expensive experiment. But remember, back then, diamond was not as precious as it is now. It wasn't until the De Beers, you guys should read that, consolidate all the diamonds and made it more precious than it's worth. Anyway, carbon plus oxygen, guess what those diamonds turn into? It went up into thin air. It turned into carbon dioxide. So yeah, you can burn diamond and all you get is worthless. You'll be contributing to global warming, in other words, CO2. Anyway, let me just finish up with this and then we'll call it quits, and then I'll continue on with this next time. What influences the speed of the reaction? The amount that you have. The more that you have, the more these things will combine and react. So that certainly helps the speed of the reaction, the concentration. Okay, and then the physical state. You guys know that if you have powdered sugar and you put it in water, it dissolves faster than if you have cubes of sugar. And that's because when you have powdered sugar, there's more surface area. So the physical state certainly is important. When you have a cube of sugar, what happens is the interior sugar are not exposed to the solvent, and so they don't have a chance to dissolve until the outer layers is dissolved away. So the physical state plays a role. The temperature. What happens is that for a reaction to take place, they have to have collisions. They have to have efficient collisions. So how do you have efficient collisions? You raise the temperature so these things knock each other off. And so the temperature is important. And then finally, there's something called a catalyst. A catalyst provides a different pathway for this reaction to take place. And if you can provide that without consuming the catalyst, then you can have a reaction. In fact, the reaction that takes place in our body is all catalyzed by enzymes. And though if we eat, for example, when we digest, we would never digest the food without the enzymes to break down that food in our stomach, okay, and the acid. So you need a catalyst. So these are all, yeah, you're right, Adrian, it's CO2 in terms of that question. But these are the factors that influence the speed of the reaction. And next time we'll talk about, okay, how can we express the speed of the reaction in terms of something called rate, the rate of the reaction. The reason why we need rate is because the rate law will be equal to that rate of the reaction when it's all said and done. Let's take a look at what exactly is a reaction rate. A reaction rate just tells you the speed by which the chemicals are changing. If you have remember that in a chemical reaction, you have the starting ingredients, which we call reactant, and we have the finished products, which we call products, of course. And during the course of the reaction, the reactants will disappear and the products will appear. So in mathematical terms, we put a negative for any chemical that is disappearing. The negative means that you have negative concentrations as you start progressing through the reaction. And then the positive means that you have positive concentrations as you are progressing through the reaction. So when we talk about the reaction rate, and it's usually quoted in molarity per time, molarity per second, molarity per minute, molarity per hour, okay? Um, it's really nothing, no difference than uh, rates that you are already exposed to. Rates that you have been exposed to is like the speed at which your car is running. If you are going down the freeway and you're abiding by the speed limit, you might be going 65 miles per hour. What does that mean? It means that in 1 hour time, you've covered the distance of 65 miles. Or maybe you're looking at your pay rate. Maybe you get paid, there's talk now of getting $15 an hour as the standard across the nation. And for those of you who get paid in an hourly basis, that would be great. It basically means that within an hour span, if you are employed and you are on the clock, you get $15. Okay, so you notice that there's a description, distance, or monetary amount over time. That's a rate. When you have something over time, then it determines the change of that quantity with respect to time. Okay, so that's what you see right here. You have the speed, you have a wage, or you can have a reaction rate, in which case we look at the change in the concentration. It could be disappearing or appearing with respect to time. And the concentration is generally quoted in molarity. Okay, molarity. So just make sure that, yeah, molarity. So if we don't look at the change, but we make the change very, very small, then what we have is a differential rate, okay? And for those of you in calculus, then you know what that means, okay? You make the change very, very small, infinitesimally small, and then you can do a derivative. But we won't really do the calculus. We will just look at the results of the calculus. But anyway, here's the general form that we're going to have. It's a change in the concentration of some chemical species with respect to time. Okay. So before I move on, I just want to make sure that you get a comfortable feeling of what we mean by rate and how it's related to the individual species in that reaction. And I'll try and use an example that was based on my experience. I remember when my brother was going to a college in Washington. Okay. And in the summer, what they would do is they would go to the coast and they would collect oysters. Now that's backbreaking work where you have to bend down and dig oysters and then fill a bucket. Okay. And you get paid based on the bucket. And so, like I said, you have to go out, dig down the oysters from the mud pit, and then depending on how much you gather, that's your pay rate. So one guy, he's a big Samoan guy, 6'3", very strong. He could collect 6 buckets per hour. It was pretty efficient. Another guy, Channing, okay, he could only collect 3 buckets per hour. My brother's best friend could only collect 2 buckets per hour. And if my brother had an injury, so he could only collect 1 bucket per hour. Okay, so what you see here are the rate by which someone is collecting oysters, and it's based on these buckets that you see right here, and the individual speed by each of the workers in this group. And so what I want to show you is how you normalize the rate so that what you have is a correlation or maybe an equation that relates everyone to each other. So what we have is this right here. If you can collect 6 buckets per hour, that's Isako, okay, that's his name, then it takes 1 Isako to collect 6 buckets per hour. On the other hand, Channing can only collect 3 buckets per hour. So it takes 2 Channings to equal 1 Isako, okay? And Mike, he can only collect 2 buckets per hour. So it takes 3 Mikes to equal 1 Isako to collect $6 per hour. And then, of course, my poor brother here, Will, and he can only collect 1 bucket per hour. So it takes 6 Wills to collect the same amount of Hisako. What ends up doing is Hisako starts helping out my brother. But anyway, that's for another story. You can see here how we normalize things so that we can put in an equation the relationship of each individual person to the rate by which you can collect oysters. We can also put it in this way. If we're looking at 1 bucket per hour, then it takes a 1/6 of Isako, a 1/3 of Channing, half Michael, and a whole Will to do that. Now, in a reaction, you can do the same thing, because remember, in a chemical reaction, you don't have a 1-to-1-to-1 ratio. You could have like a 6-to-3-to-1 ratio. And what you need to do is you need to normalize, at least that's where we're going, the relationship between each one. And it's not very difficult. You just use the coefficient in the balance equation. So let me go on from there, okay? But I want you to see how it's called normalization when we take a number and we make it like 100 or 1, and then we make all the individual parts equal that, okay? But let's take a look at a reaction. Let's say that we are looking at the decomposition of some chemical. And so we start out with 0.8 right here. And over time, it starts to drop. In 10 seconds, it drops from 0.8 to 0.65. In another 10 seconds, it drops from 0.65 to probably right here, about 0.55, and so on and so forth. We can actually calculate the speed by which that chemical is decomposing, because remember, the concentration is becoming less, so that means that it's disappearing. So in this particular case, we're looking at probably a reactant, because reactants decrease with time, and we can calculate the speed by which this particular chemical disappears. And so we call this species, well, C for concentration, and we look at the a time segment, a time lapse, because what you should see is that because this thing is at an arc, the speed at which the chemical starts to decrease early on is different from which the speed starts to disappear later on. The speed actually changes over time. But what we want to do is take an average. Okay, we want to take an average. And we want to know what is the average of the concentration change between the 40 and 10 seconds. So 40 is right here and 10 seconds right here. And remember that it's going to be the rise over the run. That's how you get this tangent right here, because this right here, this line right here is the speed of the reaction. Change my color. Okay, that's the speed of the reaction. So what is that slope? And the slope, if you remember trigonometry or geometry, it's the rise over the run. So the rise is going to be this right here, and that's 0.67. This is 0.6 right here, 0.67 and 0.4. So it's the, in this particular case, you actually need to take 0.67. It's just that difference, okay? 0.67 minus 0.4, and then 40 over 10 minus 10. And so if you do that, you get 0.27 over 30. And you can get a numerical value on that. And because it's a disappearance, you put a negative in front of that. So when you calculate that average rate between 40 and 10 seconds, the rate is about 0.090 molar per second. Remember that the -1 here means that when you put something to the -1, it means it's a reciprocal. So this right here, 1/2 is also illustrated as seconds minus 1. Okay, and you'll see that a lot in this particular chapter. When you put it to the -2, then it's 1/s². That is equal to s minus 2. Okay, so that's just a little bit of the math trick that you guys are exposed to in this particular section. So that's the rate between that frame. Okay, now suppose we want to find the rate and we want to narrow it down between, say, in this particular case, 30, which is right here, and 15 seconds. Well, that's going to be a more narrow, and so what you need to do is you need to calculate that slope again. So again, it's the rise over the run, and in this particular case, it's 0.6 minus 0.45, that's this right here, and then 30 and 15, that's this right here. And when you do the math, you come up with 0.0010, and you notice these two are not the same. The rate here is smaller than the rate here. You can actually, and it'll change over that period. Okay, it's very fast at the beginning, it's very slow at the end. So you have to define what section, what place you are looking at. But what you can also do is find the instantaneous rate at some point. And when you do that, then of course what you are doing is you're making that difference very, very small. And we don't call it delta anymore, we call it d. Okay, the derivative dc dt, and dc dt is just the slope at that point, the tangent line at that point. Okay, and you can actually calculate it if you do a little bit of calculus, but don't worry about that, we're not really going to go there. I just want to illustrate to you that there is a bunch of calculus involved in this particular section. I get why the value is negative. Why wouldn't they cancel out in the formula? Don't worry about canceling in the formula. Just know that if it's disappearing, it's negative. The fact that you should get that should not be there. Your number here, if you do 0.67 minus 0.40 over 10, yeah, 40, because it's the, actually what you need to remember is that 0.67 and 10 are at the 10 times, and 0.4 and 40 are at the same time. And the fact that it's disappearing just means that it's negative. Don't worry too much about trying to figure it out in the math. The math will work out. The math will work out. If you take 0.6, if you take 0.40 minus 0.67, that's a negative. Okay, that's a negative 0.27. And then if you take 40 minus 10, that's a positive 30. So you do get a negative number, and that's just to illustrate to you that it's disappearing, that the concentration is dropping. Okay, that's what it means. So let's move on. Okay, because that's how you calculate, if you have a graphic form, the speed of the reaction. So let's take a look at a specific reaction. This is the reaction of hydrogen plus iodine goes to hydrogen iodide, 2HI. And you can see that it takes one hydrogen and one iodide to form 2HI. And so what you can see is that this is disappearing. So that's a negative delta H hydrogen concentration over delta T. This is disappearing as well. So that's a negative delta I2 over delta T. But this is increasing. I mean, it's showing up, it's positive. So that's a delta HI over delta T. And the question is, how are they related to each other? How can I put them in an equation? And the stoichiometry here, that's a 1 to 1 to 2, will give you that relationship. The other thing I want to mention is that look at the graph. The graph, again, highlights the change in the concentration with time. You notice how HI is being produced twice as fast as H2 is being consumed. If you look at the slope at any point here and compare it to the slope at any point here, you're going to see it's a 2 to 1 ratio. And that makes sense because physically, for every one of these that is consumed, it needs to break apart and it needs to hook up with the iodine. For every one of the hydrogen that's consumed, you produce 2HI because there's 2 hydrogens in 1 H2. So it makes sense that this ratio is going to be a 2 to 1. And the balance equation shows you that as well. Okay, the balance equation shows you that. So clear my. So this is how we would do the relationship. The disappearance of hydrogen, okay, equals the appearance of H2. And we can say that the 1 mole of H2 over 2 moles of HI, what is that relationship? And this right here comes from the balance equation. Okay. And what you can see is that one is negative, the other is positive, and it takes 1 disappearance of H2 if you want to make this the same number to equal half the appearance of HI. Okay. Again, you put a 2 here because half of that, half of the appearance of HI is equal to 1 disappearance of H2. So we can do that by breaking this slope and making it half its value. So that's basically what we are saying by putting a 2 down there. Again, we're normalizing it. We're making it equal to each other so we can put it in a mathematical relationship. Okay, and the balance equation gives you that relationship. Use the balance equation for that. Yes, the reactants are always negative because they are always going to be consumed. Exactly. Okay, so good point. So when we finally do put it all together, whatever this rate is, okay, this rate could be like 6 moles per minute or 6 molarity. Remember the units is molarity per time. Whatever that is, depending on what you calculate here, the relationship is that for every 1 H2 that disappears, you also consume an equal amount of I2. It's the same ratio, but you only produce, if you want that to be an equal, you want the rate to be equal to each other, half HI. Okay, half HI. Because if you want to produce 1 HI, then it'll be, for every one of these that are consumed, it'll be producing 2 HI. That's the relationship so that they all equal the same number, the same reaction rate. So let's take a look at a generic equation where you've balanced the equation and now you have the coefficient in that balance equation. It's pretty easy to put, based on what we talked about, to put them in a relationship. If you've got an A, a B, a C, and a D, just like what we did with the oyster example, then you use that number or you use that coefficient to normalize things. So the concentration of A divided by the coefficient A over time is equal to the concentration of B divided by the coefficient B over time is equal to the concentration of C divided by the coefficient C over time is equal to the concentration of D divided by coefficient of D over time. You just use the coefficient so that everything is equal to one number, the same number right here. Okay, just like what we did with the oyster. In order to take 6 sacks and make it 1 sack, then we notice it takes a sixth of my friend Isako, takes half of my other friend, a third of my other friend, and then it equals to 1 of my brother. Okay, that's because you've established a relationship. So let's take a look at this, and let me just draw you a progression diagram of the concentration. So let's take a look at the production of water from hydrogen and oxygen. So it'll look like this. It takes 2 hydrogen, you need a balanced equation, and 1 oxygen to produce 2 water. So if we do this, I'm going to put some tick marks here. And tick marks are sort of arbitrary, depends on how much you have. We notice that the hydrogen will decrease. And let's just do this. Okay, these are arbitrary, but the shape is what is important. So for the hydrogen, let's say we start over here. We'll start here, and we notice that it disappears. 2 of that disappears over time. Okay, for oxygen, 1 of that disappears over time. And for water, initially you had 0, but over time, 2 of it appears over time like that, like that. Okay, so this is not quite like that. So these are the graphic forms that you will see if you were going to graph this. Now this slope right here, or this shape and this shape, are equal. Why? Because the coefficients are equal, except one is decreasing because it's a reactant, the other one's increasing because it's a product. And then this right here is half of this right here because it's only half the coefficient of 2. So that's how you would draw this scheme right here. And the reason why I'm giving you this example is because that's what your breakout will be. Let's take a look at this right here. Again, it's arbitrary. I'm just doing this. The main point is the shape. Okay, so oxygen, you notice that this is going to be produced. The product will always have 0 before the reaction start. It'll always have 0 before the reaction start, and then it'll show up. So this right here will be, this will be O2, 0 as we start, and then it'll go up. Okay, and it's going to be, it's not a straight line, because if it's a straight line, it means that the rate is going to be constant over time. It's not. It's fast in the beginning and it slows down towards the end. So let me erase that. Okay. Fast in the beginning, slows down at the end. But and then for ozone, let's take a look at that. We can start right here, but it's going to be looking like that. Okay, this is about, whereas this is a whole, this is about 2/3 the size of that. Okay, so you notice how I make it go down 2 tick marks before it plateaus out, and I make this go up 3 tick marks before it goes up, and that makes it easy on me because that's what the coefficients are. Okay, so that's how you would draw this concentration time diagram. So hopefully you can see that relationship. Okay, so if the rate of this was 10 moles per minute, then this would be 5 moles per minute, and this would be 10 molarity per minute, because it's the same. Okay, so again, when you put it in this form, let me clear this. When you put it in this form right here, then you make everything equal to 5 moles per minute. The reactants are disappearing and the products disappearing. And you notice the 2 here, 10 divided by 2 equals 5. 5 divided by 1 equals 5, and 10 divided by 2 equals 5. That's why you put the coefficient in the denominator of these concentration changes so that they all equal 5 molarity per minute. You need to make it equal. That's the mathematical relationship. So what's really going on? Let's take a look at NO2 and NO. Initially, all you have in, say, a reaction is NO2. And this is the balance equation. 2 NO2 goes to 2 NO and 1 O2. You could have like 30 moles of NO2 in here, but the ratio by which NO forms will also be 30 moles, and the ratio by which the oxygen is produced will only be half, because the balance equation tells you the ratio by which these things are related to each other. So if you have 30 here, then the ratio is 30 to 30 to 15 based on these chemicals. Now, what's going on? Let's say we look at the initial. All we have is NO2. And then as time progresses, 2 of these NO2 will form NO and O2. But notice that when 2 of this is consumed, 2 of these is produced, and only half of the oxygen is produced. Again, it's a 2 to 2 to 1 ratio. And then as time progresses, another 2 is consumed, and another 2 appears, and another 1 appears. So we're always keeping to the ratio based on the balance equation. Okay. Excuse me. What we have is this right here. This is an important diagram, because what you will see when we start talking about equilibrium is that we get to a point where we produce enough products, and then there's enough products to actually back react and return back to reactant. But this is an illustration of showing you how NO2 disappears over time, O2, NO appears over time, and oxygen disappears over time. And the concentration ratio by which they do so over time. So this is where we test your understanding. Okay, what I'm going to do is I'm going to break you out. Now, I don't expect you guys to answer the whole problem. I just expect you guys to communicate with each other, talk about the strategy. This will be a short session, and then give each other your contact information, either your email or something. Email is fine, or you can do it over Zoom, but get your names, and then you can work on it after class or before it's due on Friday. Okay, but and then just kind of talk, not so much work out the problem, but just talk to each other so that you have an idea of your strategy, and I'll show you what to think. So right now what we're doing is we're going to look at this. Remember, it's due in Canvas. If you go to Canvas and you look under activity, you'll be able to see that assignment, and the whole assignment is described. And this is the reaction. Okay, it's a pretty complicated reaction in which you have acrylonitrile, that's this guy right here, reacts with ammonia and oxygen to produce acrylonitrile is this guy right here. It's going to be produced from propene. That's this guy right here. That's propene. Ammonia and oxygen produces acrylonitrile and water. So that's the balance equation. Now, when we break into groups, you won't see this screen, okay, because your screen will be blank. So what you can do is take a screenshot of your computer when I show you the problem. That way you have it in front of you. For those of you who have a Mac, it's, let me see, Control-Shift-4. I don't know what it is for PC. You guys can help each other out. Okay, or one of you take a screenshot of this problem right here and then share it with your classmate. It's also found in the Canvas under the assignment. But let me describe what you guys are going to do. First of all, this is the main reaction, and I balance it for you. Okay, I balance it for you. Relate the rates of the reaction of the starting material and the product. So what I want here is I want to do rate is equal to the concentration of C2,3H6 over delta T is equal to the concentration of NH3 over delta T. And right now this is not equal, but how do I make it equal? Just like in the previous problem. If I want to put an equality sign here, what are the coefficients that I need to put in order to make it all equal to each other? So that's this part. The second part is draw a concentration versus time diagram. That's what we've been doing. Reactant will decrease, products will increase, like that. And you guys are going to put 1, 2, 3, 4, 5 lines. And of course, these two will be on top of each other because they have the same coefficient. But draw 5 curves illustrating the change with time for each of these chemicals. A couple of them will be right on top of each other because they have the same coefficient. So that's what this is. Then using this first equation right here, okay, if 120 moles, what we're assuming is 1 liter. So 120 moles equals 120 molar. 120 moles of water is produced in 1 minute. How many moles of propene and ammonia are consumed in 1 hour? You have this relationship right here that tells you the rate by which all the chemicals are related to each other. What you need to do is you need to calculate this guy based on molarity per time. In this case, they give you a minute, and then figure out, well, if that's the rate for water, what's the rate for propene? This is propene and ammonia. And you can see that propene and ammonia are going to be the same because they have the same coefficient. But it's going to be disappearing. It's going to be disappearing. And remember that the question is per hour, not per minute. So you got to use the conversion factor that there are 60 minutes in 1 hour. And then finally, the last question here is, if you've got 19.20 grams of oxygen, okay, so you can convert grams to moles, and it's consumed in 1 minute, how long will it take to produce 100 grams of acrylonitrile? So that's the problem I want you guys to solve. It's got parts, but it is very related to what we've talked about. The strategy here, like I said, is the rate for different species participating in the chemical reaction are related by the stoichiometry coefficient of the balance equation. And you've seen that in the previous. So we're going to break up into groups. Okay, so the session is over. Hopefully you've got your information. If you need to work alone because you can't stand your members, then just say that you've broken from your group and just turn that in. Again, it's not due till Friday. And the exercise, again, is just so that you guys will communicate with each other, get to know each other. I encourage you guys to help and teach each other, except, of course, when it comes to the quizzes and the exam, in which case you guys are on your own. But something like this where, you know what they say, if you can teach it and explain it to someone else, it means that you really know it. So I'm giving you that opportunity. Of course, if you have questions, you can always email me. So this again is just a summary. The whole idea of kinetics is to figure out the speed of the reaction. Okay, and what we just did was to establish the speed of the reaction, get a number, a quantity, and then relate it to the chemicals. What we are going to do now is use an experiment, use experimental data to determine the speed of the reaction, and then write something called the rate law. The rate law tells you how the concentrations of the chemical is related to the speed of the reaction, the rate law. don't confuse what we just did with the rate law. What we just did is showing you how the chemical species relates to the speed of the reaction. What we are going to do next is get a rate law equation that shows you the mathematical equation of how the chemicals will, if you change the chemical concentration, how that rate will also change. So this is called the methods of initial rate. Okay, so we have a reaction here. We have a reaction A plus B goes to M plus N. It's generic. That's when I say generic, it means that it's not specific. I'm just using symbols to illustrate the topic that I'm talking about. So the rate law is going to be equal to this. Remember that in our previous example, we said that the rate is equal to the change of, say, some chemical over delta T. So we're looking at the concentration with respect to time. These are this is a rate constant, and these are the concentrations, but it's the concentrations of all the chemicals combined that influences the speed of the reaction. Okay, this just tells you how this quantity is related to this value. This right here tells you how all these chemicals influences that rate right there. Okay, and the important thing that we are going to determine in this discussion is these values right here. These are called the orders. These are called orders, and the orders are not related to the coefficients. These values right here, A, is related to a coefficient, but these X, Y, and W are not related to the coefficient. You have to determine it. You have to determine it experimentally, okay? It's an experimentally determined value. So this is the ultimate goal that we want. This rate right here is that right there, which is related to these chemicals if you can measure the speed of the chemical with respect to time. So here are the definitions. C might be a catalyst. The catalyst can be in the rate law because it influences the speed of the reaction. X, Y, and W are called the order, and they generally are like powers. Like if you have 2, it means that you're taking the concentration and squaring it. If you've got 3, you're taking the concentration and cubing it. So these X, Y, and W for our class, they are integers. In more advanced class, they may not be integers, okay? Again, they are not related to the coefficient in the balance equation, and then K is the rate constant. The rate constant, and the rate constant has the unit so that when you multiply all of these together, the units of all of these together is equal to the units of rate. And remember, the unit of rate is molarity per time. If the time is in second, then it's molarity per second. If the time is hours, it's molarity per hour. So when you multiply all these values together, then you have the same unit as the rate. And that'll be clear when we do some examples. Okay. So we're looking at NO2 going to NO and O2. And this is the reaction that we're going to be studying here for the methods of initial rate. In determining the concentration of the species in a reaction, the formation of the product may interfere with the measurements. In other words, as this reaction progresses, you're going to produce products. But what happens is that the products that may recombine and force this reaction to go backwards. That's the equilibrium. We don't want that complication. So the way we measure the rate of the reaction is we look at that's why it's called methods of initial rate. We look at only about 3 to 4% of the start, and we measure the concentrations, and then that's what we call the rate of the reaction. We don't look at it when it becomes complicated because there are products forming. So this can be avoided if the reaction is studied under conditions in which the reverse reaction is negligible, and that's why it's called the methods of initial rate. Okay, so the key to this particular method is to do several experiments. You can't just do it with one experiment, but you do several experiments in which you vary the concentrations. Okay, and you allow the reaction to take place for a short period of time. Here it says 3%, 3 to 4% is fine, but you let it go for a short period of time. You measure the amount of the chemical that is decreasing, that decrease within that time lapse, and then you could establish the speed of the reaction. Okay, the result of the analysis yields the differential rate law, or the rate law, which is what we want. Okay, the experiment is such that the rate is a function of only the reactant in the reaction. Okay, in other words, the speed of the reaction is established by only the reactant that disappear, but you can relate it to the product that appears through the exercise that we just did. Okay, so let's take a look at this. Again, it's our reaction of, in this particular case, we're looking at the reverse of this reaction right here. Oops. We're looking at the reverse of this reaction, so we're going backwards. Okay, NO plus O2 goes to NO2. Determine the rate law via the methods of initial rate. What you see right here are the 5 experiments that was completed in order to get this rate law. The rate law is going to look like this. Rate, which is a concentration versus time, is equal to K, which is your rate constant. And the chemicals in this particular reaction, the reactant, it is a function of only the reactant, is NO2, concentration of NO2 over X, and the concentration of O2 to the Y. Our job is to calculate K, X, and Y. And by doing that, we will get the established rate law, an equation that gives us information about the speed of the reaction depending on how much of NO2 and O2 we have. That's the rate law. Okay, so how do we do that? We do that by carrying out, in this case, 5 experiments. We could actually get away with, since we got 2 chemicals here, we could actually get away with just 3 experiments. But in this particular case, we did 5. Okay, and let me just show you what's going on. This is the speed of the reaction, that's the rate. And these are the concentrations of these chemicals. This is NO2 and this is O2. So for the first reaction, we can say it's 0.028 is equal to K, 0.020 to the X, and 0.010 over Y. Now, you can't solve that equation. And the reason why you can't solve that equation is because you got 3 unknowns and 1 equation. Okay? What you need is, you need 4, you got 3 unknowns, so you need 4 equations to get your 4, to solve for the 4, 3 unknowns. But there's a simpler way, and let me show you that. Okay? This, like I said, Chem 201, there's a lot of math involved. So the way we do this, let me clear my slate here, is the following. We take 2 reactions. We only look at 2 reactions at a time. And we pick 2 reactions in which the concentration of one of the species is constant. Let's take a look at 1 and 2. In 1 and 2, we can see that the NO are the same, 0.02, 0.02. In other words, the only way this reaction changes is because of the changes in oxygen. Because if NO is constant, that really did not influence this change in the rate of the reaction. It was due to the change of the oxygen that caused this change to occur, because we're not changing the concentration of it, of NO between experiment 2 and 1. So we can use that to simplify the math and then figure out the value of one of the variables. Okay, so let me show you how that works. Once you do this, it'll be like second nature. You could do it in your head. Okay, this is just the wording of what's going on. You're going to pick 2 experiments, and each of the experiments will obey a rate law. And the rate law will be rate is equal to K times NO to the X, O2 to the Y. That's the way it is. And then for the other experiment, rate, because it's a different value, is equal to K. And this K and this K are equal. They're the same. Is equal to NO to the X, O2 to the Y. Now, in the 2 different experiments, the concentration may vary. Okay, so they may not be equal. But if you pick experiments 1 and 2, remember that in experiment 1 and 2, NO concentrations were equal. So what we can do now is we can use that relationship to simplify the math. So this is what we're going to do. Okay. Before I do that, I want to remind you that any number to the 0 power is 1. This is just a small math review. Any power to the 0 power, so 28 to the 0, that's just 1. You guys should know that from math. Anything to the first power is that just that same value. 28 to the first power is just 28. Okay, anything to the second power is squaring that value. 3 squared is 9. Okay. Anything to the third power is that number multiplied by itself 3 times. Now, this is a common mistake I see. What I see is I see 3 cube, and that is 3 times 3. A lot of you are just going to say 3 times 3, that's 9, because in your mind, you're going to think 3 times 3 is 9. That's not the case. This is 3 times 3 times 3. This is a common mistake I have. I see all the time. 3 cubed is 27. 3 times 3 is 9, times 3 is 27, not 9. So please watch out for that. Okay, here's how you would get these values right here doing some math. It's basically if you take these values and you do this relationship with the natural log, then the natural log of 2 divided by the natural log of 2, that's this right here, that's just equal to 1. You can calculate the coefficient just based on mathematical equations. Okay, you might not need to get to that point, but I just want to give you a math review. So with that said, here are more examples of that. Let's look at our experiment. Now we're going to pick experiments 1 and 2. And right now, that's all we are looking at. And what we're going to do is we're going to say experiment 2 over experiment 1, and we're going to write an equation that relates those two. Okay. And what I always try to do is look at the rate and put the experiment with the bigger rate on top. That way I don't have to deal with fraction. 0.057 is bigger than 0.028. So that's why I put experiment 2 over experiment 1. Then this number right here is just, well, this is the rate law. This is the rate law. This is the rate law. But this is for experiment 2. This is for experiment 1. The rate law are identical. It's just that the values are going to be different for the different experiments that was carried out. 0.057, that's right here. NO is 0.020, that's right here, to the X. That's one of the unknowns. K is also an unknown. And then for experiment number 2, that's 0.020 to the Y. Pretty easy, okay? Then look at experiment number 1. Experiment number 1 is 0.028, and for experiment number 1, NO is 0.020, and for experiment number 1, that's 0.010. Now look at what happens. The K's are going to cancel because they are the same. This will also cancel. That's why you pick experiments 1 and 2. And what you have here is 0.057 over 0.028 is equal to 0.020 over 0.010 all over y. That's the math. And this is nothing more than 2. 0.057 divided by 0.028 is 2. And this is nothing more than 2. So that's your equation. What 2 to what power equals 2? Well, y's got to be 1. Okay, y's got to be 1. You see why we pick experiments 1 and 2? Because then these guys will cancel and it makes the math easier. Well, now we know why. We know why. We know that it's oxygen to the first power. We still need to figure out what X is and what K is. We determine K at the very last step. But the way we determine X is we pick 2 experiments. Let me clear my slate here, sorry. We pick 2 experiments in which the oxygen now is constant. So we can pick these 2 right here because the oxygen is constant, or these 2 right here because the oxygen is constant, or these 2 right here because the oxygen is constant. So I can pick experiments 2 and 4, or experiments 2 and 5, or experiments 4 and 5. It doesn't really matter. You get the same result. Okay. So let's say I take 2 and 5, just for the sake of, because that's what I work out. But again, you could easily pick 2 and 4, or 4 and 5. But in this case, I'll pick 2 and 5. So what you see here is that the oxygen will not play a role in the change of the rate because they're the same. It's only the concentration change of NO that plays a role. So this is what you will see. Okay, this is the answer for the first part. So again, we're going to pick 2 and 5. So that's what we have. Again, I put 2 on the numerator because it has the bigger rate, and I put 5 on the denominator because it has a smaller rate. Again, I don't want to deal with fractions. Okay, you notice how the oxygen now will cancel, and what we have here is 0.057 over 0.014 is equal to 0.020 over 0.010 all over x. So that's 2 to the x is equal to, I believe that happens to be, let me just see, 0.057 divided by 0.014. I believe that might be 3. No, that's 4. Sorry. So this number is 4. 2 to what power equals 4? Well, 2 to the second. This has, x has got to be 2. This has got to be 2. Okay. See how the math simplifies? So now we know that x is 2 right here. So we can write a rate law. We can say that the rate is equal to K NO to the second, O2 to the first. Now, how do we calculate K? Well, the way we calculate K is we pick any experiment. Let's pick experiment number 2. Let's pick experiment number 2. We know what the rate is for experiment number 2, 0.057. We know the concentration of O2, I mean NO 0.020 squared, and we know the concentration of oxygen 0.020 first, because those are the values for experiment number 2. All we've got to do now is solve this math equation for K, and then we can calculate the K value. Okay, so that's basically what we do. We pick an experiment. In this case, I pick experiment 1. I know what the rate is from the table. I know what these concentrations are from the table. I know what the X and the Y is. All I've got to do is solve for K. And when I do that, this is the value I get. Now, this K times molarity squared. Where did I get molarity squared? That's 2 right there. And then remember, these bracket means molarity to the first, and that is equal to molarity per time. And let's say our time is seconds. So what unit times molarity squared, molarity to the first, gives us molarity per second. The only way we can get molarity per second in this unit analysis is if we had 1 over molarity squared second. By K having that unit, we get molarity per second, which is the unit that we want for rate. So you actually have to do some analysis in order to get the unit of K, just based on what the orders are in your rate law. And then you can get the correct unit for K. But that's how you would do it, okay? The correct unit of K would be, if you plug in K here, it's molarity to the -2, seconds to the -1, NO squared O2. Okay, so you can see that, yeah, there's math involved, but the math are not that complicated. It's not that complicated. So here's the problem. If we have 3 chemicals, okay, you guys can turn this in with your group work, and I'll give you a couple points bonus for that, okay? So here we have experiment 1, 2, 3, 4, 5, 6, 7. I actually have more experiments than I need. So what we need to do when we have 3 chemicals is look for an experiment in which 2 of the concentrations are constant to determine. So this might be to the X, this might be to the Y, this might be to the Z. So what experiments am I going to pick? I'm going to pick experiments 1 and 2. And when I pick experiments 1 and 2, then Y and Z will be a non-factor because they're the same. So when I do the analysis, I'm going to determine, using experiment 1 and 2, the value of X, because NH3 and O2 are the same. So it's a non-factor in terms of establishing the rate. Why, if I want to know why? Well, I need to find experiments in which C3H6 and O2 are the same. So I can look at these 2 right here. See how C3H6 propene is the same for this, and oxygen is the same for that? Well, this doubles. So by picking experiments 1 and 4, then I can get the value of Y. Okay, and then finally, the last variable to determine is Z. And so I need to find experiments in which C3H6 and NH3 are the same. So I can, let me look at this. Let's do these 2 right here, 1 and 6. In 1 and 6, the concentration of C3H6 is 1 times 10 to the minus 4. The concentration of NH3 is 2 times 10 to the minus 4. So 1 and 6, I can get Z. And that's what you need to do in order to do these problems. You've got 3 equations to solve. It's not very difficult. Okay, and then you can establish X, Y, and Z. Once you get X, Y, and Z, then you can solve for K. But these things, if you do it enough times, you could do it in your head. Let's just do 1 and 2. Let me show you how that I can do this in your head. You notice that for 1 and 2, this doubles. So that doubles. And notice that this doubles. So 2 to the X equals 2. For this right here, just not even doing the math, because the rate doubles when the concentration doubles, then X got to be 1. It's got to be 1. Okay, and I didn't even have to put it in that long form. I could just do it by inspection. That's why I always look for concentrations that are double or quadruple, because those are numbers that are easy to do. Anyway, I'm going to stop there. I think that's the end of this particular discussion. And here is, again, the acrylonitrile problem. Okay, so I'm sort of working that acrylonitrile problem for all it's worth. In this particular case, whenever you're studying rates of a reaction, you only study the chemical that you start with, and you monitor the decay. You can't really monitor the chemical that is being produced because you don't have anything to detect in the initial. So the best way to do this is to watch the decay of the reactant. In this particular case, we have propene, this chemical right here, ammonia, and oxygen. We could also have a catalyst. If this reaction were catalyzed, let's say there was a platinum catalyst in there, then we could also put platinum in here and figure out what type of concentration that might have in terms of the rate. Now, remember that even though we might have a concentration of the catalyst will basically be consumed and then regenerated sometime during the reaction so that the net change is zero. Okay, the net change is zero. If you start out with 1 milligram, for example, at the end, you have to end up with 1 milligram. Otherwise, it's not really a catalyst if it's going to be consumed. So we can have a catalyst in here if we want, and you'll see in some problems later that that's included in determining the methods of initial rate. So what I'm going to do is I'm going to number these real quick. One, oops, let me just see. One, make sure that I'm still on. 1, 2, 3, 4, 5, 6, 7. I'm just numbering the experiments, okay? And what I'm going to do is I'm going to say this is X, this is Y, and this is Z. That's the exponent for this particular problem. So the rate law is going to be the following. Rate, whatever the speed is equal to K, or rate constant, and the rate constant doesn't change unless you change the temperature. That's why it's called a constant, okay? So it's going to be the same for all these experiments as long as the temperature hasn't changed. And then we're going to look at propene, C3H6 to the X, ammonia, NH3 to the Y, and oxygen, O2 to the Z. Now, I could have easily named this A, B, and C, but you guys who are taking math know that we use the variable X, Y, and Z a lot. Anyway, in order to determine the order of X, we got to find experiments in which the ammonia and the oxygen concentration doesn't change. So in order to find that right there, I'm going to change pen here, okay? The two experiments in which only propene changes and ammonia and oxygen doesn't change are 1 and 2. So for this is what I will pick. I will select experiment 2 over 1. This is EX, okay? And the reason why I put 2 over 1 is because the rate for 2 is bigger than the rate for 1. And 3.33 over 1.66 times 10 to the minus 7 is basically 2 rather than 1/2. That's why I put the bigger rate on top. So that's the first thing that I'm going to do. That's the scheme that you want, okay? Then I'm just strategizing here. I'm going to find for Y here, I'm going to find experiments in which the propene and the oxygen doesn't change. And so for Y, what I will do is I'm going to select maybe, let's see. Yeah, here. Okay. These two right here, because by selecting these two, right, experiment 1 and 5, then the propene is 1 times 10 to the minus 4 for both experiment, and the oxygen is 2 times 10 to the minus 2. So which one's bigger? It looks like experiment 1 is bigger than experiment 5. So I'm going to put 1 over 5. Okay, 1.66 over 0.42. And then the last is I'm going to find an experiment in which, say, I'm going to find oxygen. That wasn't quite what I wanted. Okay. I'm going to find oxygen. So I think I said I don't know why I erased that. It was 2. It was 2. Let me erase that again. I'm not having very good luck with my pencil here. It was okay, 2 and 1. These two, and I believe it was 1 and 5. And then the last experiment that I'm going to select is I'm going to find the experiment in which ammonia and propene are the same and the oxygen changes. So I think I will select these two right here. Okay, change that pen to green. No, that's not good because that changes. How about this? I will select these two right here. Okay, the oxygen doubles, but the ammonia stays the same and the propene stays the same. So that'll be 6, let's see, 6 and 1. So those are the experiments that I'm going to look. And if you notice that in each of these experiments, 1 and 2, the propene doubles. So that's 2 over X. For 5 and 1, that's for ammonia. That's this 2 right here. The ammonia doubles. That's 2 over Y. And for the oxygen, that's 4 and 2. These values right here, that's again, it doubles 2 to the Z. Okay, so let's work on the propene. The propene will be the 3.33 times 10 to the minus 7 over 1.66 times 10 to the minus 7. That's just 2 is equal to 2 to the X. Two to the X. Since this is 2 and this is 2, X is equal to 1. You can do that off your head. That's what makes it easy. Let me just make sure. Yeah, I've is anyone else having audio problems? Because you might want to turn on, I think my audio on my indicator here says that I'm okay. At least I can see the microphone go up and down. Okay, so for those of you who are having audio problems, so yeah, try and log off and try and log back on. Okay, great. Now, yeah, it doesn't matter which experiment. There was a question in here. Shouldn't you be using experiment 7? Experiment 7 is going to be, in this particular case, if you take this right here, if someone asks for that, then you can see that if I use experiment 7, what happens here is that the oxygen doubles, but the ammonia decreases by half and the propene stays the same. You got to find experiments because you have 3, okay, chemicals to study. You got to find an experiment in which 2 of the chemicals stays the same and the third one changes. And it doesn't really matter whether it doubles or not because you're going to do the math. Okay, that's why I did not pick experiment number 7. Okay, so but let me just go on. So I'm calculating propene here, and so if you take a look at experiments 1 and 2, that's this right here. Okay, you're going to see that the rate for 2 is 3.33 times 10 to the minus 7. The rate for 1 is 1.66 times 10 to the minus 7. 3.33 divided by 1.66, that's 2. Okay, and then the oxygen doesn't play a role. The ammonia doesn't play a role, so I'm not even going to write that. And then 2 over 1, that's 2 times 10 to the minus 4 divided by 1 times 10 minus 4. All over x, that's just 2 over x. That's how I got that, okay? That's how I got that. This number is the second experiment. This number is the first experiment. And that's how I got that. So now I know that x here equals 1. Okay, now I'm going to work ammonia in this particular case. Doesn't matter about the coefficient. These coefficients do not play a role, do not play a role in the methods of initial rate. Okay, the only time the coefficient plays a role is when you're relating the speed of one chemical to the other. Okay, like take a look at the activity. The coefficients in the balanced equation does not play a role in these orders. These orders have nothing to do with the coefficient. So make sure you don't have that misconception. Otherwise, you're going to mess up. You're just going to go through the whole chapter 14 with that misconception, and it's going to hurt you in the end. Okay, so let me clean this and let's take a look at y. So I'm just going to erase this whole thing and I'm going to look at y. And remember, for y, that would be ammonia. I am looking at, let me just remind you that it's experiments 1 and 5. 1, 2, 3, 4, 5. So this right here with this right here. And why did I pick those 2 experiments? Because take a look at propene. That's the same, which means that it doesn't influence this speed right here, the speed right here, the 2 rates. If you take a look at oxygen, these 2 are the same as well. So again, these chemicals do not play a role on how the rate of the reaction changes between the 2 experiments. So what I will do is I'll take experiment number 1 over experiment number 5. Why? Because I have 1.66. Since both of these have the same exponent, I'm just going to leave them out, because 1 times 10 minus 7 divided by 1 times 10 minus 7, that's just 1. Okay, make the math easy for yourself. Okay, these are little things that you know. So if you take 1.66 and you divide it by 0.42, what you get is 4. Okay, it's 3.9523. But for our purpose, because these are experimental results, we round it off to 4. Okay, that's one of the things you can do in these types. So 4 is equal to, and let's take a look at, again, we're looking at experiment 1 over 5. So that's equal to 2 times 10 to the minus 2 over 1 times 10 to the minus 2. 10 to the minus 2 just cancels. That's just equal to 2 to the y. What 2 times what order equals 4? That has got to be, y has got to be equal to 2. You can do that off the top of your head. Now I know y is equal to 2. Okay, y is equal to 2. It's that easy. You can really do the problem by inspection when the numbers are clean. Let's do the third one. Okay, let's do the third one. I gotta clean this slate right here. That's a problem. I should not, well, let's do the third one anyway, okay? I already know that x equals 1, y equals 2, and now I'm going to do z, okay? And remember I said that z will pick experiment 1 and 6. This is 1, 2, 3, 4, 5, 6, experiment 6. And why? Because look at propene. They're the same. Ammonia, they're the same, so oxygen is doubled. So if we take experiment 6 and 1, then again, I want to make the bigger number on top. Both of these are 10 to the minus 7. They'll cancel out. 13.2 divided by 1.66, that is equal to 7.95. That is equal to 8. Okay, and that is equal to if you take this right here, because I'm doing 6 over 2, that's 4 times 10 minus 2 over 2 times 10 to the minus 2. That is just 2. 2 to what power is equal to 8? So 2 times 2 equals 4. 4 times 2 equals 8. So that Z is equal to 3. So now I know that I have that. So you can see that pick experiments so that the math comes out clean. If you pick experiments that makes it difficult for you, then you'll still probably get the right answer. You're just going to have to do more steps. Now, this is not a done problem. We need to figure out Z. Sorry, not Z, K. Sorry about that. K is the rate constant. So what I want to do is I'm going to clean my slate again. Okay, is right down here, I'm going to say rate is equal to K. So that's what I'm going to be calculating. And I'm just going to pick experiment number, I'll pick experiment number 1 here. Why did I pick that? It doesn't really matter which one. It's because both of these are 1 times 10 to the minus 2. It seems like an easy number for me. So I'm going to pick, it's going to say C3H6. Remember that X was 1. NH3, we said NH3 was 2. And O2, we said O2 was 3. 1, 2, and 3. Okay. So that is the rate law in its general form. And that is equal to 0.42 times 10 to the minus 7. Okay. Now what I'm going to do is I'm going to plug in values here. That'll be 1 times 10 to the minus 4. That's 1 times 10 to the minus 4. And that's 2 times 10 to the minus 2. And because I have values for all of this except for K, then I can solve for K. Remember that I'm selecting this experiment to plug in for my concentrations. Now, if you select another experiments, then those are the concentrations that you would be using, and you would use the rates that it corresponds to that particular experiment that you select. So what I'm going to do is I'm going to go ahead and bring all of this down to the denominator. That's just 1 times 10 to the minus 4 divided by 1 times 10 to the minus 2 squared divided by 2 times 10 to the minus 2 cubed. And that's K. Okay, so K, you have a calculator. It's just, I'm just going to do the bottom just to make the math easier. I'm going to put 1 to the 4th negative, and you guys should double check my math because I've been known to mispunch. 1 to the 2 negative squared. Okay, let me see, where's my square button? There it is. And then 2 to the 2 negative, and then I'm going to cube that, multiply that. So the bottom here is 8 times 10 to the minus 14. You should double check my work. 2 to the 2 negative cube is 8 to the negative 6. 1 to the 2 negative times 1 to the 2 negative times 1 to the 4 negative times, oops, yeah, it's 8 times 10 to the minus 14. Okay, so just double check that work. And now we have 0.42 times 10 to the minus 7. And I just have to do that math for K. And that comes out to 0.42 to the negative 7 divided by 8 to the negative 14. That comes out to 52500 0. That's K. Now, let's take a look at our units. Units are, well, they don't give us a time here. So if you take a look at the previous problem, I think it was seconds. So that'll be, so the rate is going to be, say, molarity per second. Rate is always going to be concentration per time. Now, what we need to figure out is what exactly is the unit for K. And the way you do that is you do unit analysis. Okay, you do unit analysis. And the way you do unit analysis is the following. Let me clean this real quick. And it's pretty simple if you just remember the order that this happens to be first, second, and third. So that means that you have a rate which is molarity per second, okay? And you have molarity from this right here, because that's to the first. You have molarity to the second, because that's second order right here, and you've got molarity to the third right there. So this is basically molarity per second, molarity to the 6. And if you do that, what you get is a unit of K has a unit of 1/seconds, molarity to the 5th. And that's basically how you would do this. So your final rate law would be the following. That's my K value. Rate is equal to 5.25 times 10 to the 5th, 1/seconds, molarity to the 5th, and then continuing on C3H6 to the first times NH3 to the second times oxygen to the third. So that is your complete rate law. Okay, you don't put a number for the rate because that's going to vary depending on the concentrations that you use. If you plug in any of these concentrations, try it out, any of these concentrations for this right here and use K, you should come up with that value. So that's how you would do this problem. It's once you get the hang of it, you'll be able to do these types of problem in no time at all. Okay, but you need to practice. So hopefully I've got everybody, I think I got everybody here in terms of making sure that you guys have that, okay? So look at activity number 5 if you're in lab, because you have a problem like that in activity number 5 in lab. So I'm gonna go ahead and do lecture notes 14.2 next, okay? That's but this is all recorded in Zoom. So if you need to go back and look at it, then you can review the tape.